tables and graphs work in a very similar way. Kind of think of graphs as a visual representation of a table of values. So that's what we're dealing with here. So a lot of this will feel familiar compared to tables. Just we're grabbing the numbers from a different visual. So what we have here are two functions, f of x and g of x. So f of x in blue, so that's the parabola. And I'm just going to mark it even more clearly on the graph itself. And then g of x is the linear function there, which is in purple. So there's our function g. All right, so what you can think of is that we have all of these coordinates for f of x given x values, and we have all of these coordinates for g of x given different x values. So f of g of 2. So what I want to do is replace that g of 2. So I'm replacing g of 2. I'm looking at when x is 2, what is g of x doing? So I'm going to do is go to my function and look at x equals positive 2, and then I want to look at my linear function where I have this output of negative 1. So what I want to do is grab the y coordinate of that value, which is negative 1. So really, I'm looking at f of negative 1 here. So I'm going to do is go to my graph now with x equals negative 1 and see what f of x is doing. So at negative 1, and then I look at my parabola, so I have this point, negative 1, negative 2, so I want to grab that y coordinate of negative 2. And that would be our value. G of f of negative 3, so I'm going to focus on f of negative 3. So with an input of negative 3, what is f of x doing? So at x equals negative 3, f of x is down here at negative 2. So I can replace that f of negative 3 with the negative 2. And now I'm going to look at if x is negative 2, where is g of x? So at negative 2, g of x is all the way up here at positive 7. So I'm going to have that output of positive 7. G of 0. So I'm going to look at x equals 0 and see where my function g of x is. So with that, I'll go to x equals 0 and then look at g of x, which is up here at positive 3. So I can replace g of 0 with 3. And then with g of 3, I'm looking at x equals positive 3. And where's g of x? And it's all the way down here at negative 3. So in the end here, we're grabbing the y values of these coordinates because that's the output of these functions. All right, this last one here, so we want to replace f of 1. So we have x equals positive 1, and we want to see where f of x is. So if we're at positive 1, f of x is all the way up here at positive 6. This is the same thing as looking at f of 6. So now I'm going to let x equal positive 6 and see where f of x is. And what I can see here is when I'm at positive 6, I don't even have the other function, but I definitely don't have f of x because it's restricted domain. It's ending at x equals positive 1. So since I'm outside of that domain there, it does not exist. So I'm going to write E in E for does not exist. So with this case, this is where the two functions are graphed on the same grid. This is going to be very similar here. We're just separating the two graphs onto separate grids. I'm just going to write at the top here k of x and j of x, just so I don't get them jumbled, because it's very important to know which functions with which. So this will be really similar, just what if they're on separate graphs, and then also we'll end with that little twist of what if we wanted to solve. So k of j of 2. So first thing I want to do is simplify j of 2. So if I'm looking at x equals positive 2, what is my function j doing? So if I'm at j of x, I'm at x equals positive 2, I'm seeing this output at negative 3. So with that, I can replace the inside of the function with a negative 3. And then I'm looking at x equals negative 3 for k of x, and my output for k of x at x equals negative 3 is right there at 0. So we get an output of 0 from that function. All right, if we're looking at k of 2, so if x is positive 2, where's my function k of x? You can see we have this output at positive 1 when x is positive 2. So here we're really looking at j of 1. And then what I'm going to do is go to the j of x function and look at x equals positive 1 and see where the function output is, and it's down there at negative 1. At k of 2, so looking at k of 2, we let x equal positive 2. We want to see where is the function output. I actually already have that point marked. When x is 2, the output is positive 1. And then, looking at k of 1, so if x is positive 1, where is k of x? And it's down there at negative 1. j of 2. So with that, we're looking at j of x when x is positive 2. So if I go to my function here at positive 2, I'm down here at negative 3. So this is the same thing as looking at j of negative 3. And now what I'm going to do is look at if x is negative 3, where's my function output? And we're up here at positive 4. Alright, so now let's look at solving. So like with the tables, we're going to work in reverse here. So what I really want to solve here to start with is just focusing on k. I want to see k of what is equal to 1. So how we did that with our graphs is we want to find all x values where we have outputs of positive 1. And how we can visualize that is looking at the horizontal line at positive 1. So let me draw that horizontal line at positive 1. And we want to look at these intersection points. So we have here, and we'll have to do a bit of eyeballing with this and just estimating best we can. So this coordinate here is, let's see, 1, 2, 3, we could say like 0.6, 0.7. Let's go with 0.6, like negative 3.61. And then this one's a bit clearer with 2, 1. So what we get are these two x values that work, negative 3.6 and 2. So we can say is that we know that we have this output of positive 1 if we plug in negative 3.6 for x. We have an output of positive 1. If we plug in positive 2, you get a positive 1 out. So this gives us our first step to solving, but we're not done yet because the x that we found right here is plug in for k, but the x we really want to solve for is the one that's plugging into j. So what we're going to do is our next step is we'll focus on the inside function and the fact that we want to be able to replace j of x with this negative 3.6 and this positive 2. So what we can do is kind of create this second part of the question, which is really at the heart of this question, is that we want to solve where does j of x equal negative 3.6 and where does j of x equal positive 2. So what we're going to solve from this is we're going to get these x coordinates where we see these outputs of negative 3.6 and positive 2. So to solve this, I'm going to do exactly what I did with that first graph, and I'm going to draw these horizontal lines. It's just I'm going to have two of them. So let's focus on the negative 3.6 first. So I'm going to be with j of x. I'm going to look at a horizontal line at negative 3.6 as best as I can draw. And what we can see is this one intersection point that when x is, let's say, 2.2, and we're estimating here, if this was a question on a written assignment or an exam, I would have this kind of window of error. Like, it's obviously not x equals 3, or it's also not exactly x equals 2. But if you did a 2.1 instead of 2.2, that's totally fine. So x is 2.2, and that gives us this output of negative 3.6. So that gives us one value for x. And then we want to look at this horizontal line at positive 2, which we have this intersection at negative 2 for x, negative 2, positive 2. So with that, we also have this coordinate x equals negative 2. And that would be our final solution. And then just as a reminder, if you're unsure, you can always check this by looking at the composite function. What happens when we take k of j of 2.2? What happens when we take k of j of negative 2? And the output should be positive 1 for both of them. So that's solving the equations using the graph.